This is example 2.1 from Discovering Design with Chemistry. The problem says, a chemist uses 32.0 grams of carbon and 32.0 grams of oxygen to make 44.0 grams of a gas, along with some leftover carbon. I'm going to pause there and go ahead and write down what I know. I'm adding some carbon and I'm adding some oxygen. I'm going to make a gas. The carbon has 32 grams I'm adding. The oxygen has also 32 grams that I'm adding. And the final thing is going to make 44 grams. I can look at these and just add them. You can use a calculator if you want. Clearly, I have some leftover, and they tell us that the carbon is the one with leftover. So I'm going to label that so I can remember this is my leftover. And the oxygen, I use all of that. So I know I'm going to make 44 grams. So this is what this is the equation that actually will matter in just a minute. Let's finish reading the problem. If she wants to make 110 grams of the same gas and have no leftovers at all, how much carbon and oxygen should she use? Okay, so we're going to pause on even thinking about the second one, unless the second sentence, the question, what we actually want to solve. And we're going to first figure out what we know from the first sentence. We know we're adding the two. We know that we have some leftover carbon. So I'm going to go ahead and rewrite the oxygen because I used all of that. And then I have to figure out what goes here. How much carbon did I use? So there are two ways to do it. You can either start with the 44.0 and subtract the 32.0 and see how much is left. And another way you can do it is you can start with the 64.0, subtract the 44.0. That will tell you the difference in how much you would have gotten if you'd used all of the carbon and all of the oxygen, and how much you actually got when you mix the two, meaning that difference between these two numbers, 64 minus 44, tells you the leftover carbon that was not used. Because the book has you subtracting these, that's the way we're going to do it. So if you subtract these, this is an easy one, so we're not going to pull out the calculator. You get 20 grams. This is if all was used. This is what we actually made. And then this is the carbon not used, or in other words, this is our leftover. So because of that, we know that this 32 grams right here, 20 grams of it was not used. You can probably do that in your head and figure out this is 12 grams, but if you can't do that in your head, you can take 32, and you can take the leftovers. So total minus leftovers equal the actual used part. And that's how we got that. The other way to do it is just, like I said, to start with the 44 grams, subtract the 32 grams of oxygen that you know you used all of, and when you subtract 44 minus 32, you would still get 12 grams, so the carbon has to be 12 grams. Either way is fine. The important thing is that you stay focused on this equation. This is the one that actually made the gas. The other one, let's use this one. The other one doesn't matter anymore. We only used it to see what we would have gotten if we'd used all of them. Don't let that get confusing. You can even scratch it out. This is not the real equation because we didn't use all of the gases. We had leftover one. So moving forward, we're only going to use what is actually used. So I'm going to erase some of this extra stuff. That way we don't have any extra numbers here that we don't need. Because sometimes when we have extra numbers and extra equations, they can get in our way and we can use the wrong numbers. Okay, so moving forward, now we're ready to solve the actual question. So if she wants to make 110 grams of the same gas and not have any leftovers, how much carbon and oxygen should she use? So we want 110 grams. So this is what we want. They didn't tell us how much of either one we need of the carbon or the oxygen, but we can figure that out because now it's just a simple ratio problem. We know that if we take 110 and figure out what we divided by, or we take 44 and we figure out what we multiply by to get 110, that's our multiplication factor. So what we're going to do is we're going to go this way and figure out what do we need to multiply by. If it were an easy number like 55, we would just double it to get 110, but it's not an easy number. So what we need to do is we need to take our 110, I'm going to do it up here so it's out of the way, and divide by the 44. These are both grams, so what I'm going to get is not going to have any unit because the grams are going to cancel out. What it's going to be is it's going to be a multiplication factor. And that's going to tell us what we need to multiply the 12 and the 32 by to get the numbers that they need to have. So let's pull up our calculator. So 110 divided by 44 gives us 2.5. So because this has 3 significant digits, this has 4 significant digits, we know that when we're dividing that we just compare the number of significant digits, we keep the one that has fewer. So 3 is fewer than 4, so we're going to keep 3. 2.5 only has 2, so I'm going to add one more 0. So we multiplied by 2.50 to get from 44 grams to 110 grams, which means we need to do the same thing to get our carbon and our oxygen. So we're going to take 12.0 and we're going to multiply that by 2.50. And then we're going to do the same thing with the oxygen to get from here to here. We're going to take 32 grams and multiply that by 2.50, which is our multiplication factor. And because it doesn't have a unit, we will still have grams. All right, so let's pull up the calculator and do those. So 12. And you can type the 0. My calculator will just erase it as soon as I type in the next number. So I'm not going to keep adding that 0. So I got 30. We remember that we have 3 significant digits here and 3 significant digits here. So that means I must have 3 significant digits here. So I have 30 grams of carbon that I'm using. And then for the other two, I'm starting with 32 grams of oxygen. And I'm going to multiply by my multiplication factor, which is 2.5. And I get 80. Again, this has 3 significant digits. This has 3 significant digits. So my 80 also has to have 3. So that's why I'm including the 0.0. I now know how much I need of each. To create 110 grams of the same gas as this one, I made the gas once, not me, but the chemist did. Now she wants to make it again. And the proportions need to be the same, because if they're not the same, it wouldn't be the same gas. So the answer to the question is she needs to use 30 grams of carbon and 80 grams of oxygen. And make sure that when you report your answers, you include all the significant digits that you need to include. Otherwise, there are points off. Okay, so now let's look. There's another one underneath that first one. It says the same chemist does a different experiment where she reacts 18 grams of carbon with 30 grams of oxygen to make 42 grams of a gas and some leftover oxygen. So we can kind of start out by laying it out to see what we're doing. We're adding some carbon, we're adding some oxygen, we're going to make some kind of gas. We don't know what, so I'm not going to write anything over here to the side. We use 18 grams of carbon and we use 30 grams of oxygen. And the result is 42 grams. If we add these two numbers together, you can see that we're going to get 48 grams, which is way too much. This is if we used all of both gases, but that didn't happen. So we know we have some left over. The problem tells us that the oxygen was left over. That means the carbon stays the same. It doesn't change. We'll figure out the oxygen in just a second. And we know that we used 42 grams to make the actual gas. So this is the actual gas made. I could also put actual equation for the mass. So this is our important equation. So again, I'm going to put a box around it so I can remember this is the important one. The other one is just for us to see how much was left over. So again, there are two ways you can do it. You can either take the 48.0 minus 42.0 and see that we have 6 extra grams if we used all of it, which means those 6 extra grams must be the leftover oxygen. So 6 grams of the oxygen weren't used. And then I could take the 30 and subtract the 6 so that I get 24. You can also start with this equation, and you can say, I have 42 grams of gas. I know that I used 18 grams of carbon, and so the rest of my gas must be the oxygen, and you can subtract that way. All right. So 24. Either way works. As long as you get the right answer in that blank, it doesn't matter which way you do it. And I throw in my extra little arithmetic stuff over here in case you want to see me work it, but it's not really necessary because you're probably going to pull out a calculator. Okay, so now we're trying to figure out if this is the same gas as she made before. So we need to compare. How can we tell if that first box and the second box are making the same amount of gas? What we can do is we can compare the ratios of what's happening. So let's take those two equations over to the side and rewrite them both. So this is, I'm going to put number 1, and this is where we use 12 grams of oxygen and 32, I'm sorry, not oxygen, this is our carbon, this is our oxygen, 32 grams of oxygen, and we made 44 grams of some gas. And then in our second equation, again, we're adding carbon and oxygen, but this time we used 18 grams of carbon and we added 24 grams of oxygen, and that gave us 42 grams of our final gas. You might be able to tell just by looking at this what some of the ratios are, but let's work it out anyways because sometimes it won't be as obvious. So we want to see what the ratio of mixtures is. Imagine making a different recipe, 2 different recipes in your kitchen. The first time you make a cake batter, and you know how cake batters kind of tend to be a little bit thin and runny, and so you have a lot more liquid compared to the amount of flour you have than if you make like a muffin batter, or at least my muffin batters. Mine tend to be a little thick, so I probably have a little bit less liquid than I would add to the muffin batter than I would for the pancake batter. So what we're comparing is one ingredient to another ingredient here, to one ingredient to another ingredient here. So when we do this, we have to make sure that we keep our Algebra 1 teacher used to say, keep your duckies in a row. So it doesn't matter how you compare them. You can even compare using this final number over here, as long as you use this final number over here. So what we're going to do is we're going to pick 2 things. So I'm going to pick, what did the book use? The book wants to use carbon to oxygen. So whatever you use, just write, oh goodness, my eraser came up. So whatever you use, make sure that you write it over here. You can write carbon to oxygen. You can write oxygen to carbon. You can write total. That's what I'm going to call this. This is total mass. You can use total mass to one of them or total mass to the other one. As long as you keep your things in a row, all you're doing is you're seeing if you get the same ratio for one to the other. So for number 1, my carbon is 12 grams, and my oxygen that I used was 32 grams. If these two are indeed the same gas, in other words, like the same recipe, I should get the same ratio when I do the same thing for the second one. If I take my, again, carbon has to go on top, oxygen has to go on the bottom. So carbon was 18 grams for the second one. Oxygen was 24 grams for the second one. Do you see where I'm getting those numbers from? I took carbon and divided it by oxygen for this one. And then I did the same thing where I took carbon and the oxygen and divided them in the same ratio for this. And now I can just pull up my calculator and see if I get the same ratios. I'm sorry, let me put my calculator over here. So 12 divided by 32 is 0.375. And that's not grams, that's just like a ratio of one to the other. The second one is 18 divided by 24, and that one is 0.75. I'm going to call it 750 though, because these two numbers both have 3 significant digits, so I need my ratio to have 3 significant digits, even just for comparing. So if we look at these two numbers, are they the same? If they are the same, that means the ratio of carbon to oxygen in the first is the same as carbon to oxygen in the second. They're not the same. That means they used a different amount. Because this number is bigger, it means the top number must be in a greater amount in the, quote, recipe. In other words, they're using a lot more carbon in one than they are in the other, or rather they're using less oxygen in one than they are in the other. So we find out, if you keep reading the rest of the example, what the two gases were that you made. The first gas is carbon dioxide, and the second gas is carbon monoxide. And so those are two totally different gases there. I think that's kind of the end of the problem. So it feels a little bit big because you have to go through a lot of steps to get to the end result of what you're going for. But with the problems, what you're aiming for is you want to make sure that you figure out, when they give you some information, you can read through the whole problem first if you want, but then go back and figure out, what do you know from the first sentence? What can you write down? Leave blanks where you don't know something. And then, are you ready to move on to the second sentence, or do you need to figure some stuff out before you do that? And just take it piece by piece. If you have any confusions about how we did any of this, I can talk more about it. You can send me an email or a text or whatever. But that's kind of the gist of it. In this problem, what we were figuring out in the first one was the ratios of the gases combined, so that we could find what those same ratios were, keeping the ratios the same, so we could find or multiply that to a bigger quantity. And the second one, we started out the same, but then we used our final equation of masses to figure out, was it the same recipe? Was it the same gas as the first? And so we had to use ratios of the pieces in each recipe to compare to the pieces in another recipe. And I'm using the word recipe, but this is not a recipe, but that feels more familiar to me. If you have more questions, let me know. I think that this one can be a little tricky from figuring out where to start and where to go with it. But there are probably more practice problems in the practice packet that you can download from the course website to try later.